and today we're going to talk about predictive notching for shaker testing. What is notching, you might be wondering? Well, notching is a type of limiting that actively changes a vibration level at a response accelerometer. So let's say we have this sensitive test article on here, and in this case, maybe we can't exceed 3 Gs here, or we know our test article is going to break. And we have this control accelerometer here. Now you might be asking yourself, well, why am I worried about it breaking? Isn't that the whole point of shaker testing? Well, you have to keep in mind that the in situ vibration environment for this might not be seeing more than 3 Gs here, right? The problem is when we clamp this thing to a shaker, it's not exactly the environment it's really in. We have a higher mechanical impedance, typically, almost always, with a shaker connection to a test article than we do with in situ environments. So that's why we have this limiting situation here, so that we can account for the higher mechanical impedance and be able to protect our test articles while still creating a vibration environment that's going to prove that our test article is going to do what it's supposed to do. Other things you can use notching for are limiting force and limiting overturning moment. Let's say you have a satellite on here with a high center of gravity. It has a tendency to want to tip the shaker over at certain frequencies when it goes into maybe a lateral resonance mode or something like that. So you can use it for that as well. Today, we're just going to talk about a pretty simple example. You might see on my webcam feed that I have a little cantilever beam on a shaker, and that's what we're going to test on. If you see the video here, my little accelerometer at the tip of the cantilever beam here, that's where we're going to limit our response. So a little bit more about notching. Why do we call it notching? Well, because when we start to limit, if you see this example here, this is my limited response channel. Normally I have a nice resonance peak here. What happens to the control and also the drive is we have this little dip or notch in the control channel. You want to keep in mind here that you can't avoid this, right? The whole point of notching is we're going to reduce our vibration level, and what happens is that the reference profile is basically ignored when this notching takes over, okay? So you can't have a control accelerometer follow the reference profile and also notch on that channel. Important thing to keep in mind. You're going to have to explain this to a dynamicist if you're doing notching and this happens, and people ask, well, why didn't follow the reference profile here? Well, because we were notching. Why do we need predictive notching? Predictive notching is the next step above regular notching, and here's an example. I have this high Q resonance on my beam here, and I limited at 10 Gs, but the controller can't react fast enough to this physical phenomenon and take the energy out in order to notch perfectly on this channel. This is why we have predictive notching. What it's going to do is modify the drive signal and modify the reference profile immediately to try and account for any of this overshoot. Because if you can see here, we have an active picture here. So if I open this up and move my cursor here, you can see what actually happened is instead of limiting at 10 Gs, I actually overshot by 0.8 Gs. Well, maybe this isn't a big deal, but if your hard limit is 10 Gs for a vibration exposure on a sensitive component and you go to 10.8, there is a good chance that you break something. So that's why overshoot can be problematic. And the whole point to predictive notching is the controller is going to try and account for this. Now, you do have another option, of course. You could just, instead of limiting at 10 Gs, limit down at 9 Gs. But the problem you run into is you don't necessarily know what your overshoot is going to be before you actually run the test. So that is the conundrum you run into with predictive notching. And so now let's go into our software and take a look at how this works. So I have my channels all set up here. I'm controlling on input 5, which is this accelerometer in the middle here. And my main response is going to be in the Z direction on channel 3 here. That's this accelerometer on the end here. So let's start off with just a basic pre-sine sweep. So here I'm going to just delete all this and start over again. And I'm going to do 20 to 500 hertz at 0.5 Gs and 0.5 Gs. And now this is a pre-sine sweep to identify resonance and stuff. It's much lower than our actual test level, which we're going to run at 2 Gs. And now we'll run a little pre-test here. And this is going to send a flat broadband random signal out to the shaker and tickle it a little bit and make sure all our sensors are working and everything. Okay, so here we go. We can start to see this time signal here. We can see the time signal, the response. This is our control channel, and you can see if I go to our response at 0.3, right away you can see that this level is much higher than what our control channel is, as one might expect with the resonant beam. So we'll take a look here and just double check our coherence, and we can see our coherence is pretty good here. Just gonna fix this limit here so you can see I'm not really good coherence across the board here. Always important, especially in a sine test, to have good coherence. All my pre-check stuff is good here. And I'm going to move on to this system verification and just take a look at what I'm working with here. And you can see right away with a half a G input, I am going to get a little more than 5 Gs of response here. And that's what my test prediction is showing. So here's my input, here's my response. So now let's run the actual sine sweep. Electrons flying through space. Now I've added some additional information here to look at. This is all the responses from all the channels. And in order to do that, I've created a new picture in this plot. And I go up here to Open Data Explorer and then go down to Online Data. And I can open my sweep information and my spectra, and I can just highlight and drag all these right into the plot. Now we're ready to go. I'm going to hit start, and we can see what's going on. So I've got my level increasing here, ramping up, and here we go off with the sweep. So now we can see the responses building down here, and you can see this response channel really taking off. Now, any one of these response channels can be used for limiting, but of course, the biggest response is accelerometer. Now, we do have this response here, which is in the X direction, which is an off-axis response, and sometimes you might want to limit that as well, especially if you're concerned about overturning moment or something like that. So that's about 1.5 Gs, 1.6 over there. That's really the only other point that exceeds the scroll channel there. All right, so you can see this sweep here. We did our pre-sweep, so we've identified where these resonances are, and we can kind of extrapolate, right? If I wanted to do a 2G sweep, my level might be multiplied by 4 times or something like that. And I don't want to have 20 Gs of response. Maybe I want to have half that. So you can see my largest resonance peak here, about 5 Gs. And again, my excitation was 0.5 Gs. My real test, I'm going to run at 4 times this level at 2 Gs. So using a basic notching, okay, I'll go back into my sign setup. I'm going to hit edit reference profile, and I'm going to increase to my full level. I want to run this at 2 Gs. That's my test spec. And I'm going to put this 10G limit on the profile here. So now let's see what happens when we go and run this. Okay, now if I could run this system identification all over again, but my setup hasn't changed. Only my full level test level has changed. So I'm not going to run this again. I'm going to go into my system verification, and then I'm going to use my last system identification to run this test. Okay, so I've hit calculate here, and now you can see with the increased level where the system is predicting it's going to see notching. And here is channel 3, where we have our 10G limit, and we've cut this off. Okay, so let's go back into sign control and see what happens. So I'm going to hit arm again, and I'm going to hit start. We're going to take off again. Now 2 Gs, you can see in the video how much more intense this test is than the previous one. Here we are approaching this resonance. So now you can see right away, I'm starting to notch, but I have overshoot here. And that can be a real problem. So let's see again what happens in this next resonance. Whoa, lots more overshoot there. Okay. So that's, you can see the green line is our limit, and now we've overshot by a G. Keep going here. Is this again? That's X, the X direction. All right, so we can see here that we have this overshoot, and that's no good. So this is where predictive notching comes in. So if I go into my worksheet here, I've loaded my limit prediction, and that's in add-ins. Here we go. Notching and limit prediction. That costs 21 tokens. And let's see how this works. I'm going to load my data, active section, and run 2. And now I'm going to load my profiles. Okay. I'm going to pick my drive as the reference here. There we go. So now you can see here, problem, I put my 10G limit in, where I'm overshooting here. And this is how this works. Now we've got the actual drive, and we can see what we have right now and what it will look like with predictive notching in place. So now we can see how these responses are going to look. All right, so now what I'm going to do is I'm going to hit update. Now what you can see is back in the sign setup, my profile has been modified to account for overshoot. So now let's run this test again and see if we do any better here. Again, I'm going to go back to system verification. Again, running this again, since my setup hasn't changed at all. I haven't moved an accelerometer. I haven't tightened or loosened any bolts. I haven't done anything with my setup. This is really important to understand. If something changes with your physical test setup, you've got to run the system identification again. Very important. But since nothing's changed, I'm just going to calculate with this new setup, and I can see here my responses should be good. So go back into sign control here, arm, and now run this test again with our new limits. Okay, and here we go. Now we can see we've done much better with the overshoot. Here we hit this next resonance. Again, still some overshoot, but much better than where we were at. So you might ask yourself, well, I'm still getting overshoot, so what's the point here? Well, let's go back into the limit prediction, and we have a tool here to account for nonlinearity in the structure, because essentially that's what's happening, folks. We've got nonlinearity in the structure, and the system can't predict for that. So that's where human thought comes into play here. Okay, so I'm going to go back into this notching and limit prediction, and this is the same situation as before. Now, what I'm going to do is put in this prediction margin here, and this is going to give me an extra safety factor. You can see where I was, and the blue line is now where we're going to be with this prediction margin. So maybe let's even go 1.5. Okay, and pull that down a little further. So I'm going to hit update again. All right, and now this has changed again my setup, and I'm going to go back and calculate and go back into sign control, and we'll run this again. So remember, we were overshooting still by about 0.36 Gs, and we've reduced that value even further with our overshoot prediction. And we can see how that's affected the responses. If you look in this middle graph down here, I've got no overshoot anymore. Same thing here with this resonance. I've reduced that overshoot. Maybe I was a little too conservative with that 1.5 G or 1.5 dB margin, but rather be over conservative than have the finger pointed at me for something breaking on the shaker. But you do have to balance this with the idea that we still want to get this level as high as we can without having any overshoot. So we've run this again here and we can see this better situation. Now, one other thing that you might be thinking is, well, hold on a second here. I just ran this sine sweep at my full test level 3 times. Aren't I over testing my product if I was only supposed to run 1 sweep? Yes. Okay. So this is the other function here where the notching and limit prediction can be used on a lower level sweep. So let's see how that works. One other thing that I'm going to do here is I'm also going to show you how to set up the notch profile. I didn't quite do that before. I'm going to set it up on a different channel. I'm going to limit also on this channel here. Okay. So if we take a look, this is 0.1x. So now we can go back into our sine setup and we're going to go and define a notch profile. I'm going to call this, I'm going to create a new one here. But create a new one, I'm going to call it 4G limit. And again, you don't have to define this across the whole frequency range. Limit profiles typically are limited to a band where you expect the resonance to occur. So let's take a look at how that works. I'm just going to hit cancel here and go back into my sine control and take a look at what this band is. So let me put in this double cursor and see where I'm at. So let's just say 115 to 130 is going to be my limited band for my notch profile. So 115 to 130. So I'm going to limit that and call it 4G limit. And then 15 to 130 hertz. Okay. And now I'll put in my breakpoints. It's also worth noting that you can shape the profile if you want as well. This has the same functionality as your reference profile. So if you had a limit that you wanted to have different levels for, like let's say I wanted to have 10 Gs on one resonance and 8 Gs on another resonance, I can just define that all the way through the spectrum here. So for instance, if I had another resonance at 150 to 200 and I wanted to have 2 Gs, I can set it up like that. And I just have to modify that as well. So you can see how that works. But back that out. And I'm going to hit OK here. And now I've saved this profile and I can go back to my notch limits and apply that here as well. Now, for demonstration's sake here, I'm going to take these notching limits out. Let's say I don't have any idea where these resonances are going to be. I'm going to come in here, I'm going to reset this table again, I'm going to start with my 0.5G sweep, and let's just treat this like we're starting from scratch. This is going to be my pre-signed sweep. I'm going to hit OK. And now, again, I could run a system identification again, but again, my setup hasn't changed, so this transfer function isn't going to change. So I'm just going to reuse that same setup. And again, you can see what I'm predicting is going to happen based on my transfer function. And now I'm going to call this pre-sign. Okay, and we'll hit start. Again, this is what we did already. We're doing this a second time to illustrate how this works soup to nuts. I have these responses here. I could also overlay that response up on the top as well if I wanted to. So if I go back to online data, sweep, harmonic spectra, and I'll take my response and pop it in there. I do get a kick out of watching these 5 tests. I'd sit here and watch this all day long. All right. Okay. So my pre-signed sweep has completed. So now if I go to notching and limit prediction, I'm going to load my data, my pre-signed data, sweep 1. Now what I can do from here this as well. So all this is pre-signed. So now what I can do is, did I click a little too fast there? Okay. So now I've got this, I'll check this as a reference profile, but what I'm going to do is I'm going to hit this and I'm going to edit my reference profile to my full level, and I'll hit OK. Now we can see how that's been modified. Okay. And now I'm looking at this and I can see, okay, I definitely need to notch here. This is my frequency response function. Here's my predicted response. And if I put a cursor on here, I can see, okay, my product can't take more than 10 Gs. So I have got to do something about this. Okay. Go back to my 1 dB prediction margin. And what I'm going to do is I'll load a notch profile now. So I have my 10G limit. And now we can see my notch with my 1 dB prediction margin built in. And I'm also going to this channel. So I'm going to put my 4G notch, limited notch here as well. Okay. So now I've done all my homework here, looking at what's happening and what the prediction's going to be. Okay. And what I'm going to do is hit update. Okay. And now that's locked everything into my sign setup. So we can see my limit here. And again, just to prove, I'll put a cursor on here and okay. Yeah, I'm at my 2 Gs, or I can hit reference profile and see that I'm in my 2Gs here. You can see my notch profiles are loaded. And let's go back to sign control after, of course, I calculate my system verification sequence here. Sign control, and let's watch the magic happen. I'm excited. Okay, so what I can also do in this top channel, since I'm limiting on that other channel, I'm going to put this other channel in as well. So we can see I have my notch profile here. I guess I should have stuck with that 1.5 dB. Well, I guess the lab manager is going to call me upstairs and rap me on the knuckles a little bit. So we could go to Navigator here and actually take a look at what we just did versus sweep 4. I pull in my last sweep and the one before that. And overlay them. See a little bit of improvement there. All right, well, that is my presentation, and here is my contact info. Find me on LinkedIn. I post some articles every once in a while, and of course, feel free to visit our community site. Some great articles that you can use to improve your testing game.